Professor. This is Tosh. I'm actually just trying to turn in some of my homework. So, here's the problem. One classic theme of science fiction is twin planet, Planet X, to Earth. It's a twin planet to Earth that is identical in mass, energy, and momentum, and is located at an orbit of 90 degrees out of phase, so that it is hidden from the sun, or hidden from the Earth by the sun. However, because of the elliptical nature of the orbit, it is not always completely hidden. Assume that the twin planet is the same Keplerian orbit as Earth in the same manner that it is in aphelion when Earth is at the perihelion. Calculate the first order of eccentricity E and the maximum angular separation of the two and the Sun as viewed from the Earth. Could such a twin planet or twin be visible from Earth? Now suppose that the twin planet has an elliptical orbit having the same size and shape as Earth, but rotated 180 degrees from the Earth's orbit, so that Earth and the twin are in perihelion at the same time. Repeat your calculation and compare the same situations. So what I did was I didn't know how to start, and I just wrote down some basic information. Blah 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 blah, and you can read that. All right, cool. Now to do the proof, well, let me show you what I basically looking at these two problems are. Is one is we've got a planet, and I'm going to make my planet on the left, planet Earth, and then this planet over here to be the twin planet. And this guy is at perihelion when this guy is at aphelion. That's basically the furthest point of the ellipse as opposed to the closest point of the ellipse. And when those guys go, they kind of whip around and they have the same orbit path. But notice how on the initial conditions I actually had to start this thing a little bit faster, body 2, because when it's going over here it moves a little bit faster. And I didn't get it completely to match up exactly, but I got pretty close. Alright, and then for the 2 ellipse problem, that one is a situation like this, where you have 2 ellipses, and then these guys, like for example, there's my perihelion, and they're both at perihelion at the same time, and you kind of zip around like that. And this one almost looks like they would be 180 degrees out of phase, or basically 180 degrees in angle apart, so they would never really see each other, or at least that's what this simulation looks like. So here's what my argument is. I kind of took the Kepler's second law argument, which I don't know if it's a cheating way, but whatever. Kepler's second law basically states that the areas that are swept are equal with equal time. So basically the planet that is, like I said, the planet that is closer to the perihelion will be moving faster at that given time than the planet that is closer to the aperihelion. And I think that would be good enough proof to say that those two planets won't be able or will be able to see each other when they're on the same ellipse. I tried doing some mathy stuff. I hope that all of this notation is correct. And basically, I'm saying that the area swept out as a function of time, or with respect to time, is equal to 1/2 the radius of the Earth, and that's basically the distance that the Earth is from the Sun squared over d theta dt. And this is kind of like my omega. It's like an angular velocity. And so I basically kind of said that the area swept out is equal to 1/2 the radius of the Earth at that given point in time times like an arc length, so L dot of E. And I guess that could be confusing because L is angular momentum, but hey, I didn't think about that when I made up those variables. For the twin planet, we have pretty much the same expression, and I took the ratios of those two. Well, first I said the dAs equal to each other because that should be, that's what Kepler's law states. And then I took the ratios of the two, and I basically said that the distance, the arc length distance covered over time should be equal to 1. The ratio should be equal to 1 when the radius of the Earth, the distance that the Earth is from the Sun, is the same as the distance that the twin planet is from the sun. But in an ellipse, this is almost never really the case. So therefore, they are not going to be 180 degrees apart from each other. For the ellipse planet, for the second scenario, it almost looks like this. They will be. And the reason is I set it up the way they had it, where the sun's in the middle. We got the two perihelions, and then these guys are zipping around. And of course, the sun is at the foci of the ellipse. This kind of says to me that since they're sweeping out equal areas, they'll go the same amount of distance, because the radius is relative to the time at that particular time will be the same for the Earth and the green twin planet. So that's kind of my hand wavy proof. I'd like to do a more mathematical proof, but I feel like I need a little bit more time to solve that one out. So what I ended up doing was I ended up taking those videos, and here's my same ellipse, and I tracked it. And basically what I did is I basically extrapolated XY data from the thing, and my pinwheel of death is up, so I'm trying to, there we go, it's extracting out that data. Here's my, my Earth, and then my twin, and then the sun. I actually, put the sun at the origin, even though I tracked it. I just wanted to get any small perturbations that happens, because I think that the sun will move. I mean, I know that the sun is 200, mass 200, and the bodies are 0.001, and so they're really small. But I still think that the sun will move just a little bit, so I want to take into account those small perturbations. For the ellipse, I tracked that as well. There we go. That's what the pictures look like. It's pretty cool. Cool program. And I took that XY data and I threw it out into my I wonder why I have to. Anyway, I threw it out into my Excel spreadsheet, and I just basically did some calculations. I have the XY position at a given time. During that same exact given time, here's my XY position of the simulation that I ran, and so I have it calculating out the slope from that XY position, the angle that it makes, and I even wrote down which quadrant it's in according to the Cartesian version. And I did a slight calculation here just to kind of show that the simulation is pretty accurate. I said, okay, you have your radius, which is calculated by the just straight up distance formula. I've got my dr, which is actually, I think, a dl in my case, where it's like the small arc length, and it's basically the distance formula between these 2 points right here. And I said, okay, my area is the area I'm approximating as half of this triangle, 1/2 base times height. And I know that this is an approximation, but what I really want to see is if this area swept out is the same as that area swept out. And for the most part, these values should be the same, and they kind of jump all over the place, but I feel like that is because I'm doing these approximations using this tracker, and this thing doesn't always take, this thing, the data set could be off just by a little bit. Where am I? There we go. All right. Okay, I want this one. But what I did notice is that like 348, 359, 111, 112, 922, 954. So the area swept out is actually very, very close. And when I took the averages of this entire column, then the averages ended up being pretty similar. So I'm pretty pleased with that. And this is just basically stating Kepler's law, where the area swept out over a given equal amount of time is going to be the same. Using the slope of the line that goes between the Earth and the Sun, so I call it slope ES, and the slope between the twin and the Sun, using that I was able to find out the slope of the angle that is in between the two planets. So if I found out the equation of this line and I found out the equation of that line, I can get the angle that those two lines make together. And I think that is what the problem is asking for with the calculation angle. Although I don't think I solved it out completely analytically, I just did it numerically for now, and I'm still kind of working on it. So actually, I'm kind of requesting more time at this point. I'm going to try to go as quickly as I can because I know I'm running out of time. Here's the graph of the full period, and the graph kind of goes, just to see a little bit more of how it goes. It goes up like this, and then it kind of comes down like this, and this is like the plot of the actual position, XY position of the Earth relative to the, and then the gold is the angle. Here's the twin planet, and it looks almost identical to this one, but of course it started over here and not over here. And this is the angle that I got, the gamma separation, which is what I called it, is the angle, the smaller angle in between those two planets. And if this thing is 0, then those things are exactly 180 degrees you know what I mean, apart from each other, and you can't see each, you know, the other planet. But these numbers don't go to 0 very often, almost never. I mean, maybe here, but that's pretty, they're pretty radically not 0. So anyway, that's my analysis of that one. And then I also did for the case of the double ellipse, that would be this guy right here, and I looked at those. And the interesting thing is I basically did the same exact analysis, but the angles that I got were very, very close to 0. The greatest angle I got, and actually I didn't get that, I didn't calculate that, so let me just do that now, equals maximum, I think that's the right command, there we go. What is the biggest number you can get? And it gets a little dicey over here because I'm not sure why. I have to analyze that. There we go. We'll just do it there. 3.73 degrees. So they the angle in between them is up to 3.73 degrees, which might be enough. I mean, if you consider these things point particles, then this thing would be, you know, I mean, then obviously it would be visible. But see, that's the second part of my analysis is, and I'm working on this too, is essentially I want to figure out if based on the smaller angle of separation, will someone on Earth be able to see someone on this twin planet? I'm going to assume that the planets are not point masses and they actually have a radius. What I'm not going to account for is any funny business, what I call, like, I don't know, the bending of light around gravity. I mean, I just don't know enough physics to really take care of that. Or, you know, the glare. Basically, you know, like, if you're a person standing here and you want to take a look and you can see just the edge of this planet over here, technically you wouldn't really be able to see it because the sun would be so bright that it would probably be lost in the sun, but I'm not taking that into account. I'm assuming that these are, you know, perfectly spherical bodies that that are uniform in mass density, that aren't bright whatsoever. You can just see them. And so I kind of figured that, all right, now I'm going about this in a pretty complicated way, and I haven't finished my analysis on this, so I apologize. But if we have the Earth, I basically, anything that has a capital R is talking about the radius of a planet or a large body, a celestial body, and then anything with a lowercase r is talking about the distance from that thing, is basically my radius of orbit. And I noticed, and I made up some angle beta, and I don't know, I just called it like the blind angle. What is beta such that if the Earth is, or if the planet is anywhere in this region right here, you will not be able to see it from Earth because the sun is blocking it. And that's a function of how big the Earth is, how big the sun is, and how far away you are from the sun. So my beta, or at least I recognize a little triangle right here, and the height of this triangle is the radius of the sun minus the radius of the Earth. And in order to figure out beta, or half of beta at least, I just figured, okay, well, that's the tangent of beta is equal to the height over the adjacent, the opposite over adjacent. And beta is actually 2 of them because you have 2 of such said triangles like that. And so I think that beta is actually twice this value right here. So this is my beta. I'm still working on relating that back to gamma and saying, okay, here's my angular separation, and the angular separation is always measured. It's not this one, but in the formula that I use over here, it's the smaller of the two angles. You know, how does this, where exactly can, what is the maximum value that gamma can be such that the you can still see, or you wouldn't be able to see, the twin planet would just barely be hidden from the Earth. And I'm trying to see whether or not that is, well, I guess with this particular case, with the double ellipse, I need to figure out whether it's about 3.73 degrees. And if it's bigger than that, and it could be, very well could be. I mean, because the picture is deceiving, because the radius of the Earth is much bigger than what I drew in the picture. And so, maybe at 3.73 degrees of separation, you can actually see that thing. So I'm working on it, and that's what I got so far. Thank you.